Okay. Uh, this is the 30th of March, 2026. I'm doing POTD. Should put this on the charge. Alright. Check if strings can be made with equal operations number 2. So this is the sequel of yesterday's. So I'm assuming it's going to be like more than 4 characters. Yeah, okay. You're given two strings, S1, S2, both of length n, consisting of lowercase English letters. You can apply the following operations. Okay. You can apply the following operations on any of the two strings any number of times. Choose any two indices, I and j, such that I is before j, and the difference is even, so they can't be equal. So you can't have I equals j. Oh, that wouldn't make sense anyway. But like, yeah, so it needs to be, j has to be 2 away, 4 away, 6 away, like that, and then swap them. Return true if you can make the strings S1 and S2 equal and false otherwise. So, yeah, this is very similar to yesterday's, but it's extended to have strings of length n and an even instead of j minus 1 should be, sorry, j minus I should be even, not j minus I should be 2. So if we look at this example, we see that C and that A can be swapped. And then that A and that B can be swapped. I'll write it down. Oh, that's the wrong side. Sorry. Okay. So what is this? 2840. 2840 POTD. So yeah, if I take this example, S1 being ABC, ABC DBA, ABC DBA versus S2, the target, which is cab dab, very good. Right? So if I just take S1 and I play around with it, what we see is, yeah, if we swap this C around with this A, that difference in positions is even, so that's legal. Now the C is in the right place. If I swap this A and this B, then those are in the right place. And then 1, 2, 3, 4. I'm allowed to swap this A and this B around because the difference in their positions was even, right? So it's not about being a difference of 2 anymore. 1, 2, 3, 4. The difference in positions is even, right? 5 minus 1, so that's legal. And therefore, S1 transforms into S2, and then we get true. A, B, E, B, E, A. So that's interesting. So S1 equals A versus B. So this is sort of, by inspection, we can kind of immediately tell that this won't work because this B has to get to this A, right? This B has to get to the 0th position. 0, 1, 2. But since it starts at 1 and we're only allowed to swap with even number of, we're only allowed to do because B is in position 1 and we're only allowed to swap between positions where the difference is even. No matter whatever swap we do with B, the position it ends up in will always be odd. In this case, it's not actually allowed to move anywhere because there's no even position. There's no position that is 2, 4, 6 like that positions away. So B actually won't be allowed to move in this case. But in general, if you're starting at an odd position by swapping around like this, you're always going to stay in an odd position. And since the target is in an even position, you're in trouble. So the question then becomes, how do I do this efficiently? Because that's like one rule. So like if original letter is on an even position, but its target position is odd, then return false, basically. Same with the opposite case. So if the original letter is on an odd position, but target position is even, then return false. Same thing, right? So basically just applying this logic in general. So we have like a case as to when we can return false straight away. If we find that, yeah, there's one B over here, which is an odd position, and there's there's a B over here that's in an even position. Or maybe it's better to say, if there's a B in an odd position and there isn't a B in an odd position in the target, then you can return false, kind of thing. So that's like one way. But I'm pretty sure even if we had I think I saw an example like this yesterday where you could have something like this, where it's like A, B, C, D, E, F, G. 1, 2, 3, 4, 5, 6, 7. No, I think it was just F. I think there was 6 letters. And the target involved like the A being here, the B being here, maybe the F being here. 1, 2, 3, 4. 2. Oh wait, no, I said the A was here already, didn't I? C is here. D is here. E is here. Like that, sorry. In this case, if I copy this, what happens? So S1 comes down here. I'll just label the points as well. 0, like the positions, 2, 3, 4, 5. So if I take, for example, I know that the A needs to be over here. So there's an A here, and I swap the E over here. That's legal because 4 minus 0 is even. The E in turn should go, that's an E, should go over here with the C coming back. C is in the right place. I guess the B can go over here. D can go over here. And and then D and F can swap. So maybe that's it. It's just a matter of making sure that you always have, I suppose, an even, like if the original position is even, then the final position is even. Now this gets a little bit trickier with duplicate letters, I think. So like if S1 is like, imagine you have one A here, and another A here, and then B and then C, right? And then S2 is, maybe I'll put an extra letter, D. So like 0, 1, 2, 3, 4. So there's an odd and an even. There's an even and an odd, I should say. But if I put them both on even positions, the A's, and C is like here, C is like, yeah, here, D is like 1, 2, 4 here. To be fair, the B also fails, I guess, because the A's sort of take the even positions. One of the A's, like, you know what I mean? Like, if there's a B here, it also wants an even position, but the A took both even positions that were left, and the D also took one as well. So that's interesting, actually. Is that something I can use? Like, you know, when you have n characters, half of them will start on even positions, roughly, and half of them will start on odd positions, right? Whoops. Which I think means the second like one of them swaps, A for example swaps 0, 1, 2, 3, 4, like this A started on odd position, became an even position, that B will also naturally, like one of the even positions will now go into an odd position. You know, it'll happen in pairs, I think. I'm not sure if that's super important, but it's something to observe, I guess. But anyway, in this case, we would see that, yeah, like there's an A that this A has, a couple of options. It could be mapped to this one or maybe to this one as well. But this A in turn has 0 options, right? It doesn't have another A to go to because both of the A's are in even positions. The other thing to be careful about is, let's say they both start in even positions. So S1 is like A, and then B, C, D. And S2, so 0, 1, 2, 3, 4. S2 is like B, I don't know. Let's say that the A stays, B goes over here, but then there's another, but the other A goes like here, C goes here, D goes here or something. So obviously the C is going to fail, but also this A is fine, right? It maps to an even, but this B is fine because it goes over here. This A, there's a risk that I think that, oh yeah, the A can go here, but this A is already taken, so I shouldn't count it, so the only A left is here, which is bad because this was even and this became odd, which is bad. So I'm pretty sure this works. I could be wrong. I don't know if I'm missing something, but I feel like intuition tells me that I think this should be enough. So now it's just a matter of being able to compute all this efficiently. So basically, I want to define kind of a function or some kind of procedure such that given a particular position I, where I is a valid index basically, consider S1 at I, and if there exists a position in S2 such that, we'll call it J, such that S2 of J is equal to S1 of I, so it's the same letter, and they're both either even or they're both either odd, S2 mod 2 is equal to I mod 2 is equal to J mod 2, and of course the condition that J has not been used yet for a previous, that's referring to this particular example where this A was already used, so you can't use it again, then f of I equals true. Else f of I equals false. And then the overall function, the answer we want, if f of I ever returns false, then return false overall, because that means that there exists a letter in S1 that can't be mapped to S2, else return true. All right, so we now need to figure out how to compute fi really well. Like, how can we really quickly figure out if f of I is true or false? One thing I forgot to check. Okay, 10 to the 5, yeah. So you want linear time basically. So we have all this, and then my thinking would basically just be maybe iterate through S2, for example, and find, okay, look, for a particular let's say we make a hash table, big shock, and for each, the keys are letters, B, C, D, and the values are little lists, right? 2 lists of size 2, which maintain a count, which is how many odd and how many even. So in this case, and we're iterating through S2. S2 would have, 1A in the odd, sorry, 1A in the even, that one. So that's a 1. And then 1A in the odd, 1. And then C would have 1C in the even. I think I got my things mixed around, but has 0 in the odd, sorry, and then 1 in the even. B has 1 in the odd and 0 in the even, and D has 1 in the even, 0 in the odd. And basically, this allows for a relatively quick lookup. So every time I iterate through S1 and say, okay, you know, I have an A in position 0. Do I have any A's in an even position in S2? Yes, I do. And then I'll decrement when I find it. B, I have a B in position 1, which is odd. Do I have any odd position B's? Yes, I do. So I decrement by 1. And then A has a position of 2, which is even. Do I have any A's that are even in S2? No, I don't. I did, but I decremented, right? So that says 0, and that accurately reflects the situation. So then I return false from the f function. I call it a function, but it's just like, I don't mean it like a programmatic function. I mean it's like a math kind of function. But I return false, or I report false. So therefore, overall, the whole function should return false. So I think this is it. I'm worried that I'm missing some kind of edge case where this doesn't work, but I can't off the top of my head think. I'll write it out and then just think a bit harder about it. So hash table is equal to this. For I need to learn how to use the default dict stuff and all that, but whatever. For C and S2, I should enumerate as well. So for each, knowing the index and the character, if C not in HT, if I mod 2, how do I want to do this? I really need to get better with hash tables, like just writing them out in Python, because I feel like I could make this a lot easier for myself. I say this a lot, but I've never think to do it. If C is in the hash table, then HT at C at the index I mod 2, which will return 0 or 1. So this should actually be swapped around. Sorry, in hindsight. This should be here, and this should be here. And in turn, all these values should have been swapped around. Like I shouldn't have, So we're doing even first because I mod 2 will return 0, so the index 0 should be even. If I is even, then I mod 2 will return 0, which is the 0th column, plus equals 1. Else, HT at C is equal to 0, 0. So what I can say is HT at C is equal to 0, 0. No, I can't. I'll reset everything, won't it? And then I run this. Sorry, no. If C is not in HT, that's what I wanted to do, then write this. And then just run this line. Okay, so I'm quite confident that this should handle the original construction of this hash table when iterating through S2. We put something in there if it doesn't exist, and then we increment the relevant side depending. Okay, good. From there, we simply say for I C in S1, enumerate, if C is not in HT, first of all, then return false, because we got a problem. Because basically this character in S1 doesn't even exist in S2, so you're not going to be able to transform it. Otherwise, we can safely access this key. If HTC I mod 2 is equal to 0, then return false. That's saying that we don't have access to, we don't have any more of, for example, if I is even, then we're saying, okay, do we have any of this particular character in the even position? If it's equal to 0, the answer is no, and therefore we return false. Else, I don't need an else, but whatever. Else, decrement by 1. And if we get through this entire thing and nothing bad happens, then we can return true. Sorry, not false. So that would be my understanding of the question. Um, is it correct? Who knows? I'm worried that there's some kind of like strange edge case that I'm missing. But I can't think what it would be. It would be one with like a lot of duplicates, like I don't even know. CB A CB A ABC ABC. That wouldn't fail because yeah, the same number of odd and evens are there. Like that wouldn't fail. I think maybe I should just check for the sake of it. Yeah. How small can n be? 1. Just check the small cases. Sometimes they can be the ones that mess you up more than anything else. Acceptance rate is 60% as well, which isn't super low. That's relatively reasonable, but it's also like, I mean, there's not many people who submitted, to be fair, but still, I'm like kind of wigging out. Am I missing something? I might be. I feel like I should be. Wait, how many? There's 4 A's and there's 3 B's. I think I back it. I can't think of where else there'd be an edge case, so I don't want to. Okay. Oh, it's quite slow, to be fair. It's not particularly quick. Okay, so the general idea is correct. Should I try prove this? I feel like it shouldn't be too hard. I don't know. Maybe I mean, this was more gut instinct than anything, but I want to basically prove that the correctness of this part. Like I can, if fi returns false, then I can safely, so where f is this idea of needs to find a position j such that all these conditions are true. And then I can safely be like, if fi ever returns false, then I can safely return false from the whole thing, otherwise return true. I think the false thing makes sense. Like, if fi ever returns false, you should definitely return false. I like back that a lot. That's like, I'm not even bothering to prove that because that's like just based on the common sense we had up here. Like if the original letter is in a even position and the new letter is in an odd position, then you definitely have to return false. My only thing is like, just because you didn't find that false case, can you confidently say that you can return true, like without any other checks? You know what I mean? Like in this, I mean, the fact, I mean, I got it right, so I guess the answer is yes. But like, what is the diehard like definitive proof that like, okay, there's nothing else to check? Because I just based that for me, it was just an instinct, right? Like it wasn't like I didn't have like a foolproof thing. Other than like it just felt logical, but there should be something, right? Something I can say that just means like, oh, there's no way. Maybe like contradiction, like suppose there exists a set of strings s1 s2 such that fi returns true all the time, and yet somehow the transformation isn't possible. What would be like, I don't know, maybe contrapositive? Suppose that, wait, so what am I trying to prove? I'm trying to prove that fi returns true for all I. That proves that yeah, probably is what it is actually. So if I want to prove the contrapositive, so my original required to prove is my function returns true for all I in the range 0 up to n minus 1, right? So contrapositive would be, oh, sorry, I didn't finish the proof. So this implies that S1 swaps with S2. So the contrapositive says S1 does not swap or does not transform into S2, implies that there exists an I such that f of I equals false. So this is what I'm basically claiming is like if S1 could not possibly swap to S2, there must exist sort of a position where the Fi would return false because like you have an even but there's only odd ones available. Like you have an even position but the only odd ones are available, kind of thing. I don't know, something about S1 does not swap into S2 implies that there exists a position such that Fi would return false. So, I mean, the structure would be like, suppose S1 does not transform into S2, and then it would be like, oh, by way of contradiction, suppose Fi equals true for all I. Consider some character. Ooh, that could be interesting. Consider. Wait. Okay, I don't know if any of this is correct, but consider one character in S1 and its corresponding character in S2. Corresponding meaning like the equal character that is in either the same or a different position. We know there exists this character because Fi should equal true. Consider one character in S1 and its corresponding. Create. Wait. Let me just give some letters. So, at position I, and then it's at position J, right? So, create a string S1 by swapping position I and J, right? Call this S1 prime, right? And basically, notice that we have basically the same situation. S1 prime f of j at S1 prime would equal true because S1 at prime j is equal to S2 at j. It's the same character, so like there's no problems there. And then f of I will also equal true because f of equals true for S1 prime because f of I equals true for S1, i.e. the difference in position between sorry, I'm wigging out, but this doesn't make sense. I just need to write it out properly. F of I for S1 will be true, like for this new string S1, because f of j was true for the original S1, meaning the difference in position between S1 at j and the corresponding character was even. So because the difference in between the SJ character for S1 and the corresponding character was even, the difference in position for this character that's like now in S1 prime and S2 will also be even because S1j moved an even number of places. I don't know if this made any sense, but it makes sense in my head. Like now I see the proof. So basically, what I'm saying, it's more like an induction proof actually. It's like um, if k is the number of out of place characters from between S1 and S2, then number of out of place characters between S1 prime and S2 is like at most k minus 1 because you specifically moved the ith character to its correct position. So you definitely reduced that number by 1, maybe by 2 because the jth character you swapped it with could also have gone in the right place, but at most k minus. So you're continuously, so repeating this process will get k to equal 0, i.e. the S1 prime, like eventually after enough transformations, will equal S2. So, okay, if I was to write this out properly, because this is more like scrap working, right? But if I was to do this properly, I don't know if it would be I think I wouldn't bother with the contrapositive. The first way works. The original thing is better. So I would propose that fi equals true for all I, and then I would aim to prove that this is true, that S1 can transform into S2. So I would say, yeah, suppose, since suppose that this is true, and then I'd say conduct some swap between character at position I and its corresponding character at position J. And therefore, we know that the character that was moved into the correct spot now is, in the correct spot. And the character that was moved just sort of arbitrarily into a new position will still have an even discrepance, like its difference between its position and its corresponding position in S2 will also still stay even because it was originally even and it moved an even number of times. So it will stay in even. So f of I for this S1 prime will stay true. And f of j for S1 prime will be true because it's moved to the correct spot. So that's proof. That's irrefutable. Now I'm confident. Now I want to see what you're meant to do in terms of, oh, yeah. See, this is the issue. I'm not good at this stuff. Although, what? What does this actually do? S1. So you're taking all the even increments and taking, yeah, so you're saying, so this is saying start at index 0. Wait, no. I know that this 2 is saying increase by 2 each time. I know that that's what that's saying. Interesting. Yeah, okay. So you're basically making 2 hash tables, or 4, I guess. But it's like faster because you're using like the inbuilt stuff. Fine. Conceptually the same, but yeah, okay, fine. I don't know what that's about, but fine. I guess these are examples. And then, yeah. Cool. Okay, but conceptually the same, so very good. And we've got proof, which is good.